7.1. The logarithm defined as an integral. The outline of this video is as follows. We will begin by taking a completely new approach, defining the natural logarithm function not as an inverse, but as a specific integral. From this integral-based definition, we will see how the special number e arises naturally, and then explore its fundamental properties. With our new definition in hand, I will show you how to find the derivative and integral of the natural log of x, which follows directly from the fundamental theorem of calculus. Next, we will use this logarithm function to formally define the exponential function, e to the power of x, as its inverse. Finally, we will use this inverse relationship to derive the rules for the derivatives and integrals of exponential functions, completing our rigorous development of these important mathematical tools. I will now introduce a more rigorous way to define logarithms and exponentials, which is essential for building a solid mathematical foundation. Our previous approach relied on intuition and looking at graphs, which is not always precise enough, especially for concepts like irrational exponents. To fix this, we will use calculus. We will start by defining the natural logarithm of x, written ln of x, as the area under the curve 1 over t, an idea that comes directly from the fundamental theorem of calculus. Once we have this solid definition for the logarithm, we can then define the natural exponential function, e to the power of x, simply as its inverse. This new starting point allows us to formally prove all the properties of these functions with complete certainty. Let us establish a solid foundation for the natural logarithm by defining it as the value of a specific integral. We define the natural log of x, written as ln x, as the definite integral of the function 1 over t, evaluated from t equals 1 to t equals x, but only for positive values of x. Geometrically, if x is greater than 1, you can picture the natural log of x as the area under the curve y equals 1 over t between 1 and x. If x is between 0 and 1, the integral flips its bounds, so the natural log of x is the negative of the area from x to 1. This definition immediately shows us that the natural log of 1 must be 0, because the integral's starting and ending points are identical. We use the variable t inside the integral simply to avoid confusing it with the upper limit, x. The essential idea is that this familiar function is fundamentally the accumulated area under a simple curve. I will now use our integral-based definition of the natural logarithm to formally identify the important number e. Because the natural logarithm is a continuous function that covers all real numbers as its output, we know there must be a unique input value that results in an output of exactly 1. We define this special number to be e. This means the natural logarithm of e, which is the integral of the function 1 over t from t equals 1 to t equals e, is precisely equal to 1. The clearest way to picture this is with the area under the curve. E is the point on the horizontal axis where the area under the graph of y equals 1 over t from 1 to e is exactly 1 square unit. This is the same familiar constant, approximately 2.718, that serves as the base of the natural exponential functions. So what you should remember is that e is the unique number whose natural logarithm is 1. Now I will show you one of the most elegant results in calculus: the derivative of the natural logarithm. By applying the fundamental theorem of calculus to the integral definition, we find that the derivative of the natural log of x is simply 1 over x. Since the domain of the logarithm requires x to be positive, its derivative 1 over x is always positive, which confirms that the natural log is an always increasing function. If we take the derivative again, we get negative 1 over x squared. This second derivative is always negative, meaning the graph is always concave down, curving like a broad arch. For more complex functions, we can use the chain rule, which states that the derivative of the natural log of a function u is 1 over u times the derivative of u. The most important thing to remember is that the derivative of the natural log of x is 1 over x. As a direct result of its definition as an integral, the natural logarithm has several powerful algebraic properties. The most important is that the logarithm of a product, b times x, becomes the sum of the individual logarithms, ln of b plus ln of x. Similarly, the logarithm of a quotient, b over x, becomes the difference, ln of b minus ln of x. And finally, the logarithm of x raised to a power r is simply r times the logarithm of x. These properties help explain the function's behavior across its full domains. As x grows towards infinity, its logarithm also grows without bound, and as x approaches 0 from the positive side, its logarithm goes to negative infinity, meaning its range is all real numbers. Remember that logarithms transform multiplication into addition, division into subtraction, and exponents into multiplication. Now that we know the derivative of the natural log, we can reverse the process to get a powerful new integration rule for a whole class of functions. Since the derivative of the natural log of the absolute value of x is 1 over x, it follows that the integral of 1 over u with respect to u is the natural log of the absolute value of u, plus an integration constant c. This leads to a very useful pattern. When you integrate a fraction where the numerator is the derivative of the denominator, the result is the natural log of the absolute value of that denominator. For instance, the integral of the fraction 2x over the quantity x squared plus 1 is the natural log of x squared plus 1. Since 2x is the derivative of the denominator, remember to include the absolute value, as the logarithm is only defined for positive inputs. The main takeaway is to always check if the top of a fraction is the derivative of the bottom. Now we can use the properties of the natural logarithm to define its important inverse, the exponential function. Because the natural log is a strictly increasing function, whose domain is all positive numbers, and whose range is all real numbers, we know it has a well-defined inverse. We call this inverse function the natural exponential function, which we write as e to the power of x, or sometimes as express of x. This definition provides a rigorous meaning for raising e to any power, including irrationals. The domain and range are simply swapped, so the exponential function accepts any real number as input and always outputs a positive number. This inverse relationship gives us two powerful equations. E raised to the power of the natural log of x equals x for any positive x, and the natural log of the quantity e to the power of x equals x for any real x. In short, the exponential function is precisely the function that undoes the natural logarithm. Now we will see that the natural exponential function has a uniquely simple derivative. Because e to the power x is the inverse of the natural logarithm, we can use the rule for differentiating an inverse to find that its derivative is simply e to the power x itself. This means the slope of the function at any point is equal to its value. The chain rule extends this, so the derivative of e raised to a function u is e to the power u times the derivative of u. For instance, the derivative of e to the power 2x is e to the power 2x times 2. This also gives us a direct integration formula. The integral of e to the power u with respect to u is e to the power u plus a constant. The key thing to remember is that the natural exponential function is its own derivative. Let us connect our new definition of the exponential function back to the rules of algebra we already know, which is important for being able to manipulate these expressions. The key insight is that because the natural exponential function is the inverse of the natural logarithm, all the familiar laws of exponents follow directly from the properties of logarithms. This means the function e to the x behaves exactly as you would expect from algebra. For instance, when you multiply two such terms, like e to the power x1 times e to the power x2, you just add the exponents, resulting in e to the power of the quantity x1 plus x2. The other rules follow a similar logic. e to the negative x is the reciprocal 1 over e to the x, division means you subtract the exponents, and raising a power to another power means you multiply them. The main thing to remember is that all the standard algebraic rules for exponents apply perfectly to the natural exponential function. I will now show you how to work with any exponential function, which is a powerful step because it connects every possible base back to our familiar natural base, e. The formal definition for any positive base, a, is that a to the power of x equals e raised to the power of the quantity x times the natural log of a. Using this definition, we can find its derivative with the chain rule. This shows that the derivative of a to the power of x is simply a to the power of x itself, multiplied by a constant factor, which is the natural log of the base a. For instance, the derivative of 10 to the power of x is 10 to the power of x times the natural log of 10. Be careful not to confuse this with the power rule for x to the power of 10. The corresponding integral formula is just the reverse process, where we divide by the natural log of a kami. The essential idea is that the calculus of a tanya to the power of x is just like that of e to the power of x, but with an extra factor of the natural log of a tanya. Now I will introduce the general logarithmic function, which is important because it is the inverse of the general exponential function we just saw. I define the logarithm of x with base a, written as log base a of x, as the unique function that undoes the action of raising a to a power. The most practical tool for working with any logarithmic base is the change of base formula, which states that log base a of x is simply the natural log of x divided by the constant value of the natural log of a. This formula is powerful because it allows us to find the derivative using rules we already know. Applying the chain rule, the derivative of log base a of u becomes 1 over the natural log of a, all times 1 over u, times du dx. For instance, log base 10 is just a scaled version of the natural log. The essential point is that you can always convert any logarithm to a natural logarithm before performing calculus. To conclude, let us review the logical chain we use to rigorously define logarithmic and exponential functions from the ground up. We began by defining the natural logarithm of x as an integral, specifically as the area under the curve 1 over t, from t equals 1 to t equals x. Using this definition, we then identified the unique number e as the value that makes this specific area equal to exactly 1. With the natural logarithm firmly established, we could then define the exponential function e to the power of x as its inverse. Finally, this solid foundation allowed us to construct the general exponential and logarithmic functions, such as a to the power of x and log base a of x, using our new definitions. The essential takeaway is that this entire family of functions can be derived rigorously from a single, well-defined integral. Let us pause to reflect on the main ideas with these two review questions. The first question invites you to explain the geometric meaning of the natural logarithm, which we defined as an area under the curve y equals 1 over t. It then asks you to connect this area concept to our specific definition of the number e, which is the input that makes this area exactly equal to 1. The second question reviews our overall strategy of using the logarithm to define the exponential function. I want you to consider what key properties of the logarithm, like being continuous and one-to-one, allowed us to rigorously define its inverse, the function e to the power of x, for all real numbers. I encourage you to pause and formulate your own answers, as this will confirm you understand how we built these essential functions from a simple integral.